Hello and welcome to lesson number 23, Integration Part 3. If you haven't seen the first part on integration, click this video in the top right here. If you have seen the first part but you haven't seen the second part, click this video in the top right here. To start off Integration Part 3, we are going to be discussing a very useful integration technique known as U-substitution. To start off with U-substitution, we are going to be first starting with the base of the chain rule. Recall the chain rule from derivatives, which says that if you have the derivative of a compound function, as in a function of a function, which I'm going to write as f of g of x, and you take its derivative with respect to x, this is going to be the first function's derivative of the second function, as in you take the first function's derivative or f's derivative, and then you input into that g of x multiplied by the second function's derivative, which is going to be g prime of x. Starting off with this expression, we are going to be deriving the basic idea of U-substitution. To start off, we have that the derivative of one function with respect to x is this function here. According to what we know on integration, integration is the basic reversal of differentiation. Therefore, given this expression here, we know that if the derivative of this function is this function here, then the integral of this function would be this function, plus of course the constant of integration. Therefore, we can write directly based on this expression that the integral of f prime of gx times g prime of x integrated with respect to x would be equal to the inner function here, which is f of g of x, so f of g of x plus the constant of integration c. We are going to call this expression 1. What we're going to do now is rearrange equation number 1 into a different format in order to show a different expression that gives us the same result as in expression number A. To do so, what we're going to do is first off write g prime of x instead of in the Lagrange notation as it's written here in Leibniz notation. Recall that Lagrange notation is where you put a prime to indicate the derivative, and Leibniz notation is where you put the d by dx form. Doing so, we can write that 1 gives us that d of f of g of x with respect to x is equal to, I'm going to keep this part for now, f prime of gx, but I'm going to change this bit and write it as times the derivative of g of x like this with respect to x. The advantage of this notation is that we have a very nice pattern that we can remember when we have this notation. That pattern is, first off, for the chain rule, the pattern that dy by dx is equal to dy by du times du by dx for some intermediate variable u. The other useful thing that we have with this notation is that the derivative of, let's say, a with respect to b, where a and b are some variables with some given relationship, is equal to 1 divided by the derivative of b with respect to a. This is exactly why I wrote it in this Leibniz notation. So then, using the simple rules on Leibniz notation here, we can see that d of gx by dx is 1 divided by d of x by d of gx. Using this fact, what I'm going to do now is divide both sides by this value here. Doing so, on the left side we have d of f of g of x, which I'm going to write without this bracket because that's some accepted notation, by dx divided by, so actually I'm going to write multiplied by 1 divided by this thing right here, which is d of gx with respect to x as its own object, and that's going to be equal to the right hand side. When we divide both sides by this thing, what we're going to be left with on the right hand side is f prime of gx. Now what I'm going to do is apply that first rule that we had, where we have 1 divided by dA by dB, it's equal to dB by dA. Using that here, we can see that what we have is d of f of g of x with respect to x multiplied by d of x with respect to d of gx. As we change g of x's value, what happens to dx's value? And on the right side, what we have is f prime of g of x. Now then, before we continue further, I'm going to make a substitution. This is the U-substitution that I was talking about in the beginning. I'm going to say let u be equal to g of x, as in I'm going to replace g of x with a certain symbol u. It's still the same exact thing, it's representing the same thing, it's just that we are now replacing with another symbol u. The reason we call it u substitution is because in practice, in actual integration, rather than what we're doing here, which is the theory proving, in actual integration, we will tend to use the symbol u as a placeholder for our value of g of x, whatever that may be at that given instant. So then, supposing we do this, we can now rewrite this expression we have up here in terms of u. Starting from the left, we have the derivative of f of g of x, which is f of u, since u is equal to g of x, so we can write that as the derivative of f of u with respect to x multiplied by the derivative of x with respect to the derivative of g of x, which is going to be u. So we can write this as dx by du. On the right side, we have f prime of gx. Since gx is equal to u, we can write this as f prime of u. Finally, we're going to be using the chain rule identity, which says that if we have one function's derivative with respect to some intermediate variable times that intermediate variable's derivative with respect to some final variable, it is equal to the derivative of the first thing, which is fu with respect to u, and then on the right side what we are left with is equal to f prime of u. Therefore, the derivative of f of u instead of f of gx with respect to u instead of with respect to x is equal to f prime of u. Now notice here, if we take this expression and we convert it into an integral, what we have is that the derivative of f of u with respect to u is f prime of u, meaning that the integral of that function f prime of u with respect to u is f of u plus the constant of integration c. And we know that u is g of x. Therefore, what we have here is equal to f of g of x plus the constant c. I'm going to call this expression here expression b. Now take a look at expression a and expression b. Expression a gives us that this integral on the left here is equal to f of g of x plus c. Expression b gives us that this integral here is also equal to f of g of x plus c. So from this we can see, from a and b we can see that both of these integrals are in fact equal to f of g of x plus c. Looking at the first integral is the integral of f prime of gx times g prime of x with respect to x, and on the other one we have the integral of f prime of u with respect to u. So therefore we can see the integral of f prime of g of x times g prime of x with respect to x is equal to the other integral, which is the integral of f prime of u with respect to u. This is the basic idea with u substitution. We can see this integral here when integrated with respect to x is equal to this other simpler integral when integrated with respect to u. The basic idea is that it would generally be much more easy to find the integral of f prime of u with respect to u rather than finding the integral of f prime of g of x times g prime of x with respect to x, mostly because it would be difficult to identify that we do in fact have the g prime of x and the form of f prime of gx times g prime of x. However, if we find the correct substitution, we can make this integral simpler as the integral of f prime of u with respect to u, which we can then notice is just simply f of u plus c. Now it should be noted here that when doing this, we need to pick the correct substitution, and by correct substitution I mean a substitution that will make our answer nice and simple to find. You'll notice here that in order to get this thing and get this simple integral, we had to choose u such that u is equal to g of x. If we choose a different u, we might not get a simple expression like the one we have over here. Because of this, it is very important in u substitution that you get a substitution that makes your integral simpler, not more complicated. We'll now look at a couple such examples where we can use u substitution and this basic principle, and we'll see which substitutions make things simpler and which substitutions don't. For our first example, let's find the integral of 3x plus 5 to the power of 7. In order to do this, we're going to be using u substitution, and the u substitution we're going to be using is u equals 3x plus 5. In this situation, this is the quote-unquote correct u substitution. In practice, what we would do here is to write out let u equals 3x plus 5. Now then, recall that for u substitution we need the format of f prime of g of x times g prime of x's integral with respect to x, and in that case that would be equal to the integral of f prime of u with respect to u. In this case, if we take u to be 3x plus 5, we have gx equal to 3x plus 5, but what we don't have yet is g prime of x. In order to write g prime of x, let's first find g prime of x. So in this context, g prime of x is du by dx. According to the expression u equals 3x plus 5, du by dx would be equal to 3, since the derivative of 5 with respect to x is 0 and the derivative of 3x with respect to x is 3. So what we need to write is the integral of f prime of x times g of x times g prime of x, where g of x or u is 3x plus 5 and g prime of x or du by dx is 3. Currently we have f prime being equal to the 7th power and g of x being equal to 3x plus 5 within this integral I. However, we do not have g prime of x or 3 inside of this integral. So we somehow need to get a 3 inside of this integral. The easiest way to do that is to simply take this integral, multiply it by 3 and then divide it by 3. To do that, what we're going to do is write the integral I being equal to 1/3 times 3 times this thing 3x plus 5 to the power of 7. And since for a constant can be taken in or out of the integral, I'm going to take the 3 on top into the integral and write that this is equal to 1/3 of the integral of 3x plus 5 to the power of 7 times that 3 all integrated with respect to x. Now we have the format that we need in order to do our u substitution. We have f prime, which is the 7th power of g of x, which is 3x plus 5 times that thing's derivative g prime of x, which is 3 integrated with respect to x. So now doing our substitution, we can see this is equal to the integral of f prime of u with respect to u, where f prime is the 7th power. So then, doing that substitution, we can see that the integral I is equal to 1/3, which is the constant here, times this integral, which is also equal to the integral of f prime of u, which is 7th power of u, so u to the power of 7, integrated with respect to u, so du. So all you have to do is evaluate this simple integral now in order to find the value of the integral of 3x plus 5 to the power of 7 with respect to x. Now then, for u to the power of 7, we know that the integral of x to the power of n is going to be x to the power of n plus 1 divided by n plus 1. According to this, if we have integral of u to the power of 7 with respect to u, it's going to be u to the power of 7 plus 1 or u to the power of 8 divided by 8. So therefore, this integral here is going to be 1/3 of u to the power of 8 divided by 8 plus of course the constant c. So we're going to write plus c. Now, this would be sufficient for our answer. However, generally, when we're doing integration with u substitution, we do not want our final answer to contain any u's. We want to convert it back to our original variable. In this case, our original variable was x, and the relationship was u equals 3x plus 5. So therefore, we want to replace any u's that we have in our final answer with 3x plus 5's. Doing so, we can see, actually, first off, what I'm going to do is take this 1/3 and this 1/8 and write it as 1/24. And then what we can see is that we have a u to the power of 8. Since we don't want any u's in our final answer, we're going to replace u with the corresponding value of x, which is 3x plus 5. Therefore, what we have is 1 divided by 24 times 3x plus 5 to the power of 8 plus c. So therefore, the integral of 3x plus 5 to the power of 7 integrated with respect to x is going to be equal to 1/24 of 3x plus 5 to the power of 8 plus c. So we can write finally that the integral of 3x plus 5 to the power of 7 with respect to x is going to be equal to 1 divided by 24 times 3x plus 5 to the power of 8 plus c. Now note, this is not the only way that we could have done this integration. We could have also taken 3x plus 5 to the power of 7, we could have expanded it according to the binomial expansion, and then we would get a polynomial which we could then individually integrate each component and get our final answer. However, rather than doing that, this form here is much simpler, which is the power of u substitution. Now that we have a basic understanding of substitution and integration, let's move on to solving some classic integrals that we need to know based on U substitution. Along the way, we're also going to learn some important rules and limitations when it comes to U substitution. To start off, we're going to be integrating 1 divided by a squared plus x squared with respect to x, where a is some element of the real numbers but a is not equal to 0. Given this condition, the appropriate substitution is going to be x equal to a times the tangent of theta, where the theta value is some element of the real numbers. This brings us to our first limiting condition. This condition is actually not exceeded here. However, in the next integral we are going to be doing, it will be exceeded. The condition is that given a value of x, our substitution variable must have some certain value corresponding to that value of x. In this case, that value is satisfied since we know that a is a constant that's not equal to 0 and theta is some element of the real numbers, and we know the tangent of theta varies from negative infinity to infinity. We have basically some constant times something varying from negative infinity to infinity. Therefore, a times the tangent of theta will hit all possible values from the real numbers when we take theta being an element of the real numbers. Due to this fact, for every possible value of x, there is a corresponding value of theta. This will not be the case for certain substitutions. For example, x equal to the sine of theta. Here, since we know that sine of theta is limited between -1 and 1, there will be no theta corresponding to the value of x equal to 2, for example. In this case, we need to place a limitation on the value of theta, saying that theta is only between, sine of theta is only between -1 and 1. Therefore, there are no thetas in the real numbers such that x would be equal to 2, for example. There are such limitations. However, in this example, x equals a times the tangent of theta. Since a is not equal to 0, there are no such limitations. For every value of x, there is a corresponding value of theta. So that rule is satisfied. Given that that rule is satisfied, we can apply this as a substitution. Doing so, the next thing we need to find is dx by d theta. We need to do this because, recall, in order to use U substitution, we need to have the integral of f prime of g of x times g prime of x. The g prime of x is what we are finding with dx by d theta. Now then, finding dx by d theta, x is equal to a times the tangent of theta. A is a constant, so it remains when we take the derivative. So we have a, and tangent of theta's derivative with respect to theta is secant square of theta. If you don't remember that, check this video on the top right here. So then, we have that the derivative of x with respect to theta is a times the secant square of theta. So what we need to do now is convert this thing into the format of having something on the front and secant square, a secant square of theta on the inside of it. Now then, considering this integral here, this is the integral of 1 divided by a squared plus x squared, and we know that since x is equal to a tangent of theta, x squared can be replaced by a squared tangent square of theta. Doing so, we have the integral of a squared plus a squared tangent square of theta, and in our substitution, instead of x, according to this thing, we need to substitute a times the secant square of theta times d theta. So therefore, instead of dx, we write a times the secant square of theta d theta. Therefore, this expression here is the substituted integral that we have. If this original integral was I, this integral here is also equal to I. Now then, in order to solve and simplify this, the first thing we're going to do is take this a squared from both of these terms, factor it out, and then take this a and cut it out. Here we can see this a squared can be factored out as a 1 divided by a squared, and this a can be cancelled with one of the a's, cancelling, so we get just 1 divided by a. Doing that in one quick step, we can write this as 1 divided by a times the integral of what's left over. What's left over here is 1 divided by 1 plus the tangent squared of theta times the secant square of theta integrated with respect to theta. Now then, here, in this thing, we know a certain identity for 1 plus tangent square of theta. It comes from the identity sine square theta plus cosine square theta equals to 1. If you don't remember that, click this video on the top right here. It says that 1 plus the tangent square of theta is equal to the secant square of theta. Making that substitution, we can see that the integral I is equal to 1 divided by a times the integral of 1 divided by the secant square of theta multiplied by the secant squared of theta integrated with respect to theta. Here we can see where the secant square of theta on the bottom and the secant square of theta on the top. Cancelling them out, we get that this is equal to 1 divided by a times the integral of this thing, which is just 1, because when we cancel everything we are left with 1. So the integral of 1 with respect to theta. And finally, we know that the integral of 1 with respect to theta is simply going to be theta. So therefore what we have is 1 divided by a multiplied by theta plus the constant c. Now then, recall that we do not want to leave our answer to our integral in terms of our substituted variable. We want to have it in terms of the original variable. In this case, we had x equal to a tan theta. Therefore, if we want to get back to our original variable of x, we need to write theta in terms of x. Rearranging this equation, we can do exactly that. What we have is that x is equal to a times the tangent of theta. Dividing both sides by a, we get the tangent of theta is equal to x divided by a. Now then, within the range of theta between negative 90 and 90, we know that the tan inverse is a proper function. Therefore, we can say that within that range, theta is equal to the tangent inverse of x divided by a. We can use this thing to substitute into here to get rid of our substitution variable. Doing so, we can see that theta is equal to the tangent inverse of x divided by a. Therefore, our final answer is going to be 1 divided by a times theta, which is the tangent inverse of x divided by a, and then of course plus the constant of integration c. As a summary, we can take this integral on the top here, which was the integral of 1 divided by a squared plus x squared with respect to x, where a is an element of the real numbers and a is not equal to 0, and we can say that this is finally equal to 1 divided by a times the tangent inverse of x divided by a plus c. Writing that out as a summary, integral of 1 divided by a squared plus x squared with respect to x is equal to 1 divided by a times the tangent inverse of x divided by a plus the constant of integration c, and of course we need to add the condition for a being an element of the real numbers and of course a not being equal to 0. Given these conditions, this integral here is equal to this expression on the right here. Moving on to the next integral. As I discussed, this integral has a range problem. This integral is the integral of 1 divided by the square root of a squared minus x squared with respect to x, where a is greater than 0. In this case, we can see there's a small issue with the square root, as if x is anything bigger than a, as in the size of the value of x is anything bigger than the size of the value of a, then x squared is going to be a bigger number than a squared. Therefore, a squared minus x squared would be a negative number, and we will be taking the square root of negative number, which is not within the real numbers. It's going to be a complex number. Furthermore, if the size of x is equal to the size of a, then a squared would be equal to x squared, meaning that a squared minus x squared would be equal to 0. We would have the square root of 0, which is alright, but then we have 1 divided by that value. 1 divided by 0 is undefined, so therefore this will also not work for x being equal to a's size. Due to this reason, we limit that the size of x should be less than the size of a. So x absolute value less than a. Here we don't need to put the absolute value of a here, because anyway we defined a to be a positive number. Now then, given this condition, we can apply a substitution, and the only reason this substitution works is because of this limiting condition here. The substitution is going to be let x equal a times the sine of theta. Now then, we know that the sine of theta is between negative 1 and 1. Due to this, a times the sine of theta will be between negative a and a. However, this is alright for us, since for this particular integral, the absolute value of x is going to be less than a, meaning that x is going to be between negative a and a. Given this expression here, this substitution x equals a times the sine of theta is going to be valid within that range. However, if x would be allowed to go anywhere outside negative a and a, or for example, let's say x equals sine of theta plus 2 for example. In this case, x could be equal to 2. X could be equal to 3, and the corresponding value of theta for that would be pi by 2. X could be equal to 1, and the corresponding value of that would be negative pi by 2. However, we could never have x equal to 4. The reason we could never have x equal to 4 within the real numbers of theta is because if x was equal to 4, we would have 4 equal to sine of theta plus 2. So therefore, the sine of theta would be equal to 2, and the sine of theta equal to 2 simply does not exist within the real numbers. Due to this reason, Sine of theta does not provide the sufficient value when x is equal to 4. Therefore, there are certain values of x for which we do not have a corresponding value of theta. However, in this simple example of this integral here, all the values of x have a corresponding value of theta because x is limited between negative a and a. Now that we established that this is a valid substitution within the ranges allowed and that there is no problem, we can continue with our integral. So then, continuing with our integral, we know that if we have the substitution, the next step that we need to do is to find dx by d theta. Dx by d theta in this case is the derivative of a times the sine of theta. Since a is a constant, it remains, and considering the sine of theta, the derivative of the sine of theta is the cosine of theta. Therefore, we need to have here the cosine of theta. Now then, let's try and figure out what we have once we do our substitution. I is equal to the integral of 1 divided by the square root of a squared minus x squared, and x is equal to a times the sine of theta. So therefore, this bit is equal to a squared times the sine squared of theta. And then we need to multiply that by the corresponding value of dx, which we can see from here. Dx divided by d theta is equal to a times the cosine of theta. So for a small change dx, the corresponding change d theta times a times the cosine of theta is equal to that value. As in, if we take this to the other side, dx change is equal to a cosine of theta times d theta change. So therefore, we can replace dx by a cosine of theta d theta. So then, this right here is the integral that we need to end up evaluating. Simplifying this out, we can see there's an a squared here and an a squared here, which we can pair up as a squared, and then we get remaining a 1 minus sine squared of theta. And we can see, since this is inside a square root, and since a was defined to be a positive value, the square root of a squared is going to be equal to a. So then here this bit is going to end up giving us a 1 divided by a and a square root of 1 minus sine squared of theta. Writing that out, this is the integral of 1 divided by a times 1 divided by what's left over, which is 1 minus the square root of 1 minus sine squared of theta. That needs to then be multiplied by this bit, which is a cosine of theta integrated with respect to theta. Now then, this a and this 1 divided by a cancel. A is not equal to 0 since a is a positive number, so there's no problem here. And what we're left with is this thing, 1 divided by the square root of 1 minus sine squared theta multiplied by cosine theta d theta. Now then, what we're going to do is to write this thing based on our identity that we know, which is that sine squared theta plus cosine squared of theta is equal to 1, meaning that cosine squared of theta is equal to 1 minus sine squared of theta. Therefore, what we have here is the integral of 1 divided by the square root of the cosine squared of theta multiplied by the cosine of theta d theta. Now at this point, what we're going to do next is to take the square root of cosine squared of theta and write it as the absolute value of theta, cosine of theta. Therefore, this is equal to the integral of 1 divided by the absolute value of cosine of theta multiplied by the cosine of theta d theta. Now here, what we're going to do in order to get rid of this cosine of theta and this cosine of theta is to understand the range of theta that we're dealing with here. In order to get all possible values of x, which is all the values of x between negative a and a, the furthest we need to go with theta is to negative pi by 2 and pi by 2. The reason for that is at negative pi by 2, sine of negative pi by 2 is equal to negative 1, and at pi by 2, sine of pi by 2 is equal to 1. Due to this, theta needs to only vary between negative pi by 2 and pi by 2. This is going to be useful later for the sine inverse that we're going to have. However, for now, we're going to take the fact that theta is only varying between negative pi by 2 and pi by 2. Considering the corresponding variance of cosine of theta, for the range negative pi by 2 to pi by 2, the cosine of theta is always positive. Due to this, the absolute value of the cosine of theta is in fact equal to the cosine of theta. Using this little bit of logic, we can get that the absolute value of cosine of theta is equal to cosine of theta. So what we really have here is the integral of cosine of theta divided by cosine of theta, because this absolute value of cosine of theta is the same as cosine of theta, integrated with respect to theta. Cancelling these out, we can see this is equal to the integral of 1 d theta, which is simply theta plus c. Now then, what is theta? According to this expression here, x equals a sine theta. For x's absolute value which are less than a, as in the size of x is bit less than the size of a, we are going to have that if x is equal to a times the sine of theta, then the sine of theta is equal to x divided by a, and since we are staying within the valid range of negative pi by 2 to pi by 2, we can also say that theta is equal to the sine inverse of x divided by a. Given all of these conditions, we can finally say that since theta is equal to sine inverse of a, that our final expression of our integral is going to be equal to theta, which is the sine inverse of x divided by a plus c. Therefore, our integral on the left, which was the integral of 1 divided by the square root of a squared minus x squared with respect to x, is equal to the sine inverse of x divided by a plus c for a greater than 0, and also for the condition that the absolute value of x only stays between negative a and a. These are two very common integrals in integration. You will very often see them in the 15th question of part 2 of the pure mathematics paper. They are very commonly used. In fact, they are so commonly used that you don't need to state the theory that you have behind them, as in you don't have to state that the integral of 1 divided by a squared plus x squared with respect to x is 1 divided by a times the tangent of x divided by a plus c. You can simply use it where applicable. Now that we've done some example questions regarding integration using u substitution, let's move on to some important theories regarding definite integration with u substitution. One of the most important ones is the idea of changing the limits. So then, to do this, we're going to bring back an old example, and that example is the integral of 3x plus 5 to the power of 7 with respect to x. Recall, using u substitution, we found that this was equal to 1 divided by 24 times u to the power of 8, where u was equal to 3x plus 5, which we could write as being equal to 1 divided by 24 times 3x plus 5 to the power of 8. Recall that the only reason we did this resubstitution of u, as in we brought back the value of u in terms of x, is because we didn't want our final answer to be in terms of an unknown variable. We wanted it to be in terms of the variable that we knew in our original integral, which in this case was x. And in this case, if I write a definite integral version of this, let's say for example, let's say we write the integral from 0 to 1 of this thing, so integral from 0 to 1 of 3x plus 5 to the power of 7 dx. This would simply be the value we get when we substitute the limits to 1 divided by 24 times 3x plus 5 to the power of 8, where we substitute the limits from 0 to 1. So basically we find this thing's value when x is equal to 1, and we find this thing's value when x is equal to 0, and then we subtract them. So we get 1 divided by 24 times the value of 3x plus 5 when x is equal to 1, which is going to be 3 plus 5, since 3 times 1 is 3, to the power of 8, minus the value when x is equal to 0, which is 1 divided by 24, times 3 times 0, which is 0, plus 5, so total 5, to the power of 8. We can see if we simplify this, we get 3 plus 5 to the power of 8, or 8 to the power of 8, minus this thing, which is 5 to the power of 8, all divided by 24. So this is the answer that we get. However, you'll notice, if instead of finding the value of x corresponding and we substituting it to here, if instead we found the value of u to be 3x plus 5, and then we found that corresponding value of u at the upper limit and the lower limit, and then substituted, we would get the same answer. What I mean here is that instead of finding the values of x and substituting them into this expression, if instead we took this expression, as in the 1 divided by 24 u to the power of 8 plus c, 1 divided by 24 times u to the power of 8 plus c, and we took its limits for the value of u when x is equal to 1, which is going to be 3x plus 5, which is 8, so 8, and the lower limit is going to be the value of u when x is equal to 0, which is going to be 3 times 0 plus 5, which is 5, and then we evaluated this instead, we would still get 1 divided by 24 times 8 to the power of 8 minus 1 divided by 24 times 5 to the power of 8, which is 8 to the power of 8 minus 5 to the power of 8 divided by 24. What I'm trying to illustrate here is that rather than finding the original expression in terms of the original variable, we could just stick with our substituted variable and find the same value of the integral. The only thing is, when we do this, we need to adjust the upper and lower limits for the value of u corresponding to the original values of x. So as in, we need to find the value of u when x is equal to 1, which is 8, and we need to find the value of u when x is equal to 0, which is 5. So then we replace the two limits. We can see that this is basically equal to the integral from 5 to 8 of the corresponding function of u, which would be 1/3 of u to the power of 7 du. My apologies, du. So from this we can see that for definite integration at least, we do not actually need to resubstitute our original substitution for u. Instead, we can find the corresponding limit for u for the value of x and then just integrate with respect to u and never come back to our original variable x. We're going to be using this technique in a few examples to show you that you can change the limits of your function when you're doing definite integration. For our first example integral, let's solve the integral from 1 to 4 of x times e to the power of negative x squared dx. In order to do this, the substitution we're going to be using is u equals x squared. So we're going to say here, let u equals x squared. In this case, the next thing we need to find is du by dx, which according to this thing is going to be equal to 2x. Now then, what I want to do is to get this x and this dx together, so I can replace it with something in terms of du. From this expression I can see, if I take this dx to the other side, I have an x times dx. I can divide both sides by 2, and then from this I can get that x times dx would be equivalent to du divided by 2. Now then, the next extra step that we have here is to change the limit, since this is a definite integral. Over here, we have x equals 1 as the lower limit and x equals 4 as the upper limit. Generally, when we are solving this kind of integral, what we would write is something like this. When x equals lower limit, which in this case is 1, we find the value of u, and then also when x equals upper limit, which in this case is 4, we find the value of u. So, when x is equal to 1, u is equal to x squared, which is going to be 1 squared, which is going to be 1. So therefore, the lower limit of u is going to be 1. As for the second thing, for the upper limit, when x is equal to 4, u is equal to x squared, which is going to be 4 squared, which is going to be 16. So u equal to 16 is our upper limit. Therefore, the integral in terms of u should be starting at 1 and ending at 16. Rewriting all of this, we can finally say now that the integral I is equal to the integral starting from the lower limit of u, which is 1, up to the upper limit of u, which is 16, of the expression on the inside. Now then, for the expression on the inside, we can take this x and this dx and replace it with du divided by 2. So here we have du divided by 2. What we have left once we remove the x and the dx is e to the power of negative x squared. And x squared is equal to u. Therefore, what we have is e to the power of negative u. So, the integral I is equal to the integral from 1 to 16 of e to the power of negative u times du divided by 2. I am actually going to take this divide by 2 out as a constant and say this is equal to half the integral from 1 to 16 of e to the negative u with respect to u. Now then, we know how to solve this integral here. It's quite simple. This integral is half times the limits of negative e to the negative u as u goes from 1 to 16. If you are confused how this happened, you really need to check the previous video on integration. This happened because we have a constant of negative 1 times u. We know that when we have this kind of thing, this is going to be e to the power of negative u divided by negative 1, which is going to be negative e to the power of negative u. Now then, for our final step to find the area under the curve here, all you need to do is substitute the value of 16 and from that subtract the value when u is equal to 1. Doing so, we get half times negative e to the power of negative 16 and then minus the upper limit, the lower limit, which is going to be negative half of negative e to the power of negative 1, and that's our answer. Now then, here we can see that this negative and this negative cancel to give us a positive. Rearranging all of this, we can see that what we have is a half times this thing on the inside, which is going to be 1 divided by e minus 1 divided by e to the power of 16. So we can write that as 1 over e minus 1 divided by e to the power of 16. This right here is our final answer. For our next example, we are going to be considering the integral from 0 to pi by 4 of the sine cubed of x with respect to x. In order to solve this thing, we are going to be using the substitution u equals cosine of x. Now, in order to make sense of why this substitution is being used, I'm first going to have to simplify this expression down into something else. What I'm going to do first is to take this sine cubed of x and write it as sine squared of x times sine of x. Doing so, we get the integral from 0 to pi by 4 of the sine squared of x times the sine of x with respect to x. the next thing I'm going to do is use the identity that the sine squared of x plus the cosine squared of x is equal to 1 for any value of x. Therefore, sine squared of x would be equal to 1 minus the cosine squared of x. Writing so, we get that this is equal to the integral from 0 to pi by 4 of 1 minus the cosine squared of x times the sine of x with respect to x. Now at this point, we're going to introduce our substitution. We're going to say, let u equal to the cosine of x, and you will see why I'm using this substitution when we take the derivative. If we consider du by dx, we can see that du by dx is the derivative of cosine of x with respect to x, which is going to be equal to the negative sine of x, and from this we can see that if we rearrange this, then sine of x dx is equal to negative du. This is the whole reason why I wanted to take u equals cosine of x, because then sine of x du of x, or this part here, will be taken care of and will be replaced by negative du. Now then, we need to do one more thing, and that is to find the values of the limits for u. For x equal to 0, u equals cosine of x, so we can say that when x equals 0, u is equal to the cosine of 0, which is going to be 1. And also, we need to find the value of the upper limit, which is x equals pi by 4. When x is equal to pi by 4, the cosine is of pi by 4 is equal to 1 divided by the square root of 2. Therefore, u is equal to 1 divided by the square root of 2. So, we have our upper limit and now a lower limit. The upper limit is 1 divided by the square root of 2 and the lower limit is 1. So, therefore, using all of this information, we can replace our integral and its limits now and write this is equal to the integral of the lower limit, which is 1, up to the upper limit, which is 1 divided by the square root of 2, of the values on the inside. Here we can see 1 minus the cosine squared of x can be replaced with 1 minus u squared, and in terms of the sin x dx, it can be replaced with negative du. So times negative 1 times du. Now then, here we can see on the inside we have a negative 1. We can actually replace that with this thing, and we can write 1 minus u squared as u squared minus 1 with this negative 1, giving us the integral from 1 to 1 divided by the square root of 2 of u squared minus 1 integrated with respect to u. Now then, what's this equal to? Well, we know the integral of u squared, we know the integral of negative 1, so we can find our answer at this point. Doing so, we can see the integral of u squared is u cubed divided by 3, and the integral of negative 1 is negative u. And this needs to be evaluated from the values of u going from 1 to 1 divided by the square root of 2. Now then, applying the limits here for the upper limit, we have to write 1 divided by the square root of 2 cubed divided by 3 and then minus 1 divided by the square root of 2. And on the other side, for the lower limit, we need to substitute 1, which means we have 1 cubed divided by 3 minus 1. Now then, cleaning all of this up, 1 divided by the square root of 2 cubed is going to be 1 divided by the square root of 2 times 1 divided by the square root of 2 squared, which is 2. So therefore, we can write this as being equal to 1 divided by 2 times the square root of 2, and then there's another 3 here which we can take together to be 1 divided by 6 times the square root of 2. And then we have 1 divided by square root of 2 here minus this thing. Here we have 1 divided by 3 and another negative 1. 1 divided by 3 minus 1 is negative 2 divided by 3. And then this minus combines with that to give us positive 2 divided by 3. Now, let's try and take all of this under a common base. The best common base we can take here is 12, since all you have to do to get 12 with this thing is to multiply by root 2. To get 12 with this thing, we need to multiply by 6 times square root of 2. And to get 12 as a base of this thing, we need to multiply by 4. Doing so, we get root 2 for the first thing, so divide by root 2 and then 6. Root 2 times root 2 gives us, actually I'll write it directly as 12. For the next thing, we have to multiply the top and bottom by 6 times the square root of 2, which gives us negative 6 square root 2 over 12. And then this thing, to get the common base of 12, we need to multiply top and bottom by 4, which gives us 8 divided by 12. Now then, taking everything under a common base, we have divide by 12. Here we have an 8, which I'm going to write as 8. And then here we have a square root of 2 and a negative 6 square root of 2. Combining that, we have negative 5 square root of 2. So then we can write negative 5 square root of 2. Hence our final answer, which I'm going to leave in this way, is going to be 8 minus 5 times the square root of 2 all over 12. Before we continue to the next lesson, I'm going to be showing you some more integrals. These integrals can be solved by u substitution. However, I'm not going to be solving them in this video. Rather, what I'm going to do is to give you a substitution that will give you an integral that is simpler to solve, and I'm going to let you use your own knowledge of integration using U substitution to try and find the integrals. I highly recommend that you try and do so. First off, what we have is the integral of sine of x to the power of an odd number, as in an odd power of sine of x. Here we can see I've defined that by saying 2n plus 1 for n being an element of the positive integers. For this case, the substitution you're going to want to use is u equals the cosine of x. As for the next case, it's something similar. It's an odd power of cosine of x instead. Again, 2n plus 1, where n is a positive integer of cosine of x. For this thing, the substitution you're going to be wanting to use is u equals the sine of x. The way you do this, of course, is the standard method, where you take u, you take du by dx, you try to turn the integral into some form of integral which has u that you can substitute, as in this case you need some kind of sine of x inside of this thing that you can, cosine of x inside of this thing that you can substitute. And if you take du by dx, for the first thing you're going to get some negative sine of x, which you're going to have to figure out and get it into the value you want. Same thing with this one, and find it. As for this third integral, here we have the integral of sine of x to the power of m times cosine of x to the power of n. In this case, there are four possible cases where we have the integral of sine to the power of m, where m is a even number, times the cosine of x to the power of n, where n is an even number, in which case you can actually reduce it simply using double angle identities. As for the other three cases, when m and n are both odd, you can use one of these things, and when m is odd, n is even, or n is odd, m is even, for those two cases, again you can use one of these two as you like. As for the next one, here we have the integral of 1 divided by a times the cosine of x plus b times the sine of x plus c. In this case, the substitution you're going to be wanting to use is u equal to the tangent of x divided by 2. Using this substitution and trigonometric identities, you can simplify this integral over here. As for this thing here, for this integral, we have 1 divided by a times the cosine squared of x plus b times the sine squared of x and plus c. In this case, what we're going to be wanting to use is u equals the tangent of x. Again, using trigonometric identities, we can simplify this using this substitution into a nicer answer. As for the next few integrals, for this first one, we're going to be wanting to use the substitution as x is equal to, let's say, a cosine theta, or we could even use x equal to a sine of theta. Both of these work here. In this case, of course, again, same thing we need to do. We need to find dx by d theta in this case, and then find a good substitution that we can use. Substitute that into this thing and find our integral. As for this one, in this case, we're going to be wanting to use x equal to a times the tangent of theta. Doing so, again, is the standard practice of using the substitution and finding the correct answer. As for the next one, here we have the integral of 1 divided by the square root of x squared minus a squared. In this case, the substitution we're going to be using is x equal to a times the secant of theta. Again, using trigonometric identities, we can use this and simplify in order to get a nice integral. For the very last two, the first one we're going to be using a substitution saying that, let's say, u is equal to the square root of ax plus b. And for the next one, we're going to be using the substitution that 1 divided by u is equal to px plus q. I highly recommend that you try and substitute like this and find the answer that corresponds to it. And good luck with doing so. The next and final thing we need to talk about in integration is something called the volume of revolution. The basic idea of volume of revolution is as follows. Supposing we have a graph y equals f of x, like this. If we take this graph and we take it and rotate it around the x-axis like so, as in we take it, rotate it like this, keep its distance from the x-axis constant and rotate it around, and when we do that, suppose we rotate it 360 degrees and enclose a certain surface like this. We have enclosed a certain surface, let's say between the points at x equals a and x equals b, and within this surface, if we consider all the volume between the curve as it moved around this surface, as in when the curve moved it created a surface, and if we consider the volume between that surface and the x-axis, we are going to have some kind of surface covered volume like this. Supposing we want to find the volume of this shape that we've created here. How do we do it? As in between the x-axis and this surface created by rotating this graph around the x-axis like so, how do we find the volume of this object that we've created here? The basic idea here is to break this volume up into thin little slices. Let's consider starting at x equals a, and let's consider moving a distance dx in the positive x direction. If we do this, we can see that for a very small dx, the general height increase dy is very small. If we ignore that small height increase and only consider this volume that we have here, we can see that we've constructed a small cylindrical surface. Within this small cylinder, we have a height dx and a radius of this thing right here, which is y equals fx at x equals a. So basically this height here is f of a. So the volume that we've created here would be this base area, which is pi times r squared, or pi times this radius, which is f of a squared, times the small distance dx. So this small volume here is, let's call it delta v. The small delta v that we've created here is basically the value of f of x at x equals a, which we will just generally write as f of x squared multiplied by pi multiplied by the height, because the volume of a small cylinder is pi r squared h. So therefore the height is dx, which I'm going to write as delta x, because we're not going to take it as being a very small volume yet. We're going to take it as being some finite large volume. We're not going to take the limit as it approaches 0. So then this small volume of this cylinder, delta v, is equal to pi times the function squared delta x. Now then, what we have to do in order to get the total volume of this cylinder, this cylindrical shape that we have here, is to sum all of these individual values of these small volumes as x goes from a up to b. That is the job of integration. So basically what we need to do is to integrate this function here from x equals a up to x equals b. Writing that as an integral, we can say that the total volume v is the integral from a to b of each of those individual slices, which were having cross-sectional area of pi times r squared by r, where r is f of x. So pi times f of x squared as we change the variable dx, as in as we change x, what happens to pi times f of x squared, and we do that from x equals a up to x equals b. So this right here is the expression for the volume in between the surface created by this graph and the x-axis. We can actually take this pi outside of this integral because pi is a constant. We generally tend to do that, and so we generally tend to write that the volume of revolution of a certain graph y equals f of x is given by pi times the integral from x equals a up to x equals b of f of x whole thing squared integrated with respect to x. We can do this for any function f of x that is valid. And that concludes the lesson for today and the lesson on integration in general. Thank you for watching and goodbye.